I've always been fascinated by electromechanical displays, the kind you used to see at train stations or airports. These days you really can't find them anymore. They've mostly been replaced by LED-based 7-segment displays or full-screen digital ones that can show pretty much anything. Objectively, that's a better solution, cheaper and less prone to breaking, but still, those displays had something special. And that's exactly why I decided to build a display that brings some of that old magic back. It won't work exactly like the ones from train station, but to display anything, you still need to mechanically move something instead of just turning LEDs on or off. And to keep up with modern times, it's gotta have Wi-Fi on board. That means you'll be able to control it remotely via web application or hook it up to any smart home system, like Home Assistant for example. This project is completely open source, so if you ever feel like building one yourself, just grab my files and go for it. And if you do, make sure to show off how it turned out. Some time ago I came across a video that really inspired me. The project was seriously impressive. I loved it, and you should totally check it out after watching my video. But as awesome as it was, I noticed some room for improvement, mainly around the assembly process. I wanted my design to be easy, fast and cost-effective to manufacture. In other words, I aimed for true design for manufacture approach, or DFM in short. I also wanted to make the whole thing as cheap as possible, in terms of both build time and parts cost. So my top priority was to simplify the build as much as possible while still keeping all the key features like saving the display state after it's powered off, Wi-Fi communication both via Home Assistant and directly, a modular and fully customizable design, I'll dive into that part in a bit, and of course those satisfying clicky sound effect when the display switches. For this video let's break down a few key terms so we are all on the same page. The smallest movable part is called a segment. You can turn it on or off independently of the others. 7 of these come together to form a module, which can display a single digit or symbol. The first module is the main one. It has the microcontroller and acts as a brain of the whole operation. The rest are the extension modules. In theory you could have as many as you want, but due to things like voltage drop and communication speed, I had to set a limit. This module here is the separator. It could be a colon, a dot, or dash, or whatever. And all of this combined makes up the display. And even though I talked about it in the singular, it can actually handle several completely independent tasks at the same time. Like I mentioned before, the project is fully open source. You can download all the files and build it yourself, totally free. Check out my website for more info. But if you'd rather save yourself some time and hassle, feel free to swing by my store. Each segment is made up of movable 2-colored flap and fixed 2-color background. By rotating the flap 180 degrees, you can switch the segment's color from white to black or vice versa. To flip the flap, I went with magnetic force. Inside the flap, there's a permanent magnet. Depending on which magnetic pole is underneath, the magnet will naturally snap into one of two positions. Of course, I'm not planning to manually wave the magnet around every time I want to change a segment. I'll be using Electromagnet for that. The guy behind tinfoil hat made his electromagnets from scratch, which is super impressive, but it takes forever, which doesn't line up with my DFM approach. So I bought a ready-made 5V miniature electromagnets from AliExpress. As my tests showed, it does exactly what it's supposed to. It's strong enough, small, and it doesn't draw too much current, which matters when you have a bunch of them in one project. The downside? Price tag. One electromagnets cost about $2. If you want a 5-module display, you are already looking at $70 just for the electromagnets. Then I remembered another awesome creator on YouTube, Karl Bugea, who is an absolute wizard when it comes to PCB embedded coils, aka planar coils. Those are basically electromagnets too, and using them solve both the high price issue and the complexity of building your own electromagnets. Plus, it wouldn't be a separate component with wires to solder and route. These coils would be part of the PCB itself, which I need anyway. The downside of this kind of coils though is that they are weaker than traditional electromagnets, mainly because they have fewer windings. And since I'd never designed such a thing before, I made a test PCB to see if it would even work. Another big downside of the PCB coils is how hot they get. Commercial electromagnets have tons of windings, so they can generate decent force with relatively low current. On a PCB, there are way fewer turns, which means you need to pump in more current to get similar results, and that leads to serious heat buildup. With some of the coils, the temperature was already pushing the PCB safe limit after just a few seconds. After testing, I did find a coil that was good enough. It draws about 0.6 amps, it doesn't heat up too fast, and it produces enough force to flip my segment flap. I decided to upgrade the display in chunks of 7 segments at the time. Basically one module after another. That means I'll need around 4.2 amps at 9 volts. So I'm looking at power supply of at least 40 watts. That's not exactly smart potatoes, but I can live with that. If you'd rather update the display one segment at a time, a 10 watts power supply will actually be enough. It will slow down the switching process quite a bit, but it's a good way to save some cash on a power supply. On the flip side, if you want to switch the entire display at once, say 4 modules altogether, you'd need something like a 160 watts power supply. So if you are building a clock and fast switching is a priority for you, you can totally do it. It's not gonna be cheap, but you can do it. The schematic isn't overly complicated, but let's talk about a few key components. The direction of the magnetic field in an electromagnet depends on polarity, just like in DC motors. So to control that, I needed what's called an H-bridge. It is basically a circuit made of 4 transistors. Depending on 2 input signals, lets you run current in one direction or the other. Luckily, you don't have to build an H-bridge from scratch. There are small and cheap ICs for that. And by small, I mean something like this. Each H-bridge needs 2 control lines. So if you are working with, say, 6 modules, that's 42 segments, meaning you'd need 84 GPIOs. That's where shift registers come in. These are simple chips that let you control, for example, 8 outputs using just 3 inputs. But you can chain them, connecting one output of the one to the input of the next. So in theory, you could control an unlimited number of outputs with only 3 pins. But in practice, you run into issues like voltage drops and increased update times the longer the chain gets. That's exactly why I had to put cap on the maximum number of modules in the display. When it came to picking the microcontroller, I didn't have to think too hard. I went with the ESP32 because honestly it's just great. And no, Espressif didn't pay me to say that. But hey, if they ever want to talk about collaboration, I'm totally open to it. The PCB for this display was made by JLC PCB. And before I go any further, I want to give them a huge thanks for sponsoring this project. To boost the inductance of the coils, I went with a 4-layer board. Instead of increasing the coil's diameter, I stacked up the layers. A 4-layer board is still considered as a basic option in JLC, so the pricing is super affordable. But if that's not enough for you, they can even make boards with up to 32 layers. The ordering process is very easy too. Just upload your Gerber files to the form on their website, select a few options you want, and hit checkout. Price-wise, as you can see, it's just a few bucks plus shipping, and if you want, they can even do soldering for you. I've been using their services for years, and I've never had any issues with quality or customer service, so I can honestly recommend them without hesitation. Thanks, JLC PCB! This is the main board. The PCB on the extension modules, it's identical. The only difference is what gets soldered onto it. On the main board, aside from the microcontroller, there's also RTC chip and a coin battery. So if you want to use it as a standalone clock, completely offline, you totally can. In this project, tolerances are absolutely critical. Each flap has to move freely, no sticking, no jamming. and obviously it can fall out either. As for colors, I went with black for housing and the off segments and white for the on segments. But of course you can go with whatever color combo you like. If you've got a printer with MMU, AMS or any other automatic filament switching system, awesome, go for it. But if you are like me and you don't have one, no worries. You can just print a white and the black parts separately and glue them together with some super glue. Since this is the main module, it only has an output connector for communication with other modules. The extension modules, except for the last in the chain, have both input and output connectors. But to show you that, I need to assemble a few of them first. Thankfully, it doesn't take too long. I was able to put them together in no time. As you can see from the outside, all the modules look almost identical, which was exactly what I was going for. The main module has an optional RGB LED to indicate status. You don't have to include it, but I think it's pretty useful. It lets you know if the device is working correctly. On the back cover, I screw in 7 bolts that might seem totally pointless at first glance, but trust me, they are not. The coils on the PCB are made of copper, which isn't ferromagnetic. That means the segments won't hold their position once the power is cut. By adding these screws, the permanent magnet inside of each flap gets something to latch onto. This way, the coil only needs to be powered for about 100 milliseconds, and then it can be completely turned off. On the housing side, where the connector is, I added those little notches and bumps to prevent modules from being connected the wrong way around. Plugging them in backwards would send 9 volts into pins that are only rated for 3.3 volts, which could end up very badly for a few components on the PCB. Don't ask me how I know that. To connect the modules, I'm using these male-to-male pin connectors. I actually used the same method in my smart home hub project and it worked great. For the mechanical connection between modules, I'm using these snap-in clips. Just press them until you hear that satisfying click and you are good to go. I wanted a modular and all-purpose design. The idea was to let you configure the display exactly the way you need it. A clock-style display, for example, is going to look different from the one that's meant to show a custom message, right? It can sit on the shelf or be mounted on the wall. The power connector can be in the first module or any other one. You might want an LED on the first module or not. All of this adds up to roughly a gazillion different combinations. To make configuration easier, I've bundled everything into one file. Just toggle the features you want or not directly in your slicer. I tested it in Prusa Slicer, but I think any modern slicer can handle this. I also made a separator module that has no moving parts. It can be something like a colon, dot, comma, or just a blank space. It's handy when you are displaying things like time or dates. Even though it's passive, it still has its own PCB, so it can pass power and control signals along to the next module. For the microcontroller, it's completely transparent. It doesn't do anything functional. Its only job is to serve as a visual or aesthetic element. If you want to arrange the display in 2 or more rows, you need to connect the last module of the first row to the first module of the next row with a jumper cable. For the microcontroller, it doesn't matter how the modules are physically arranged. As long as all 10 pins are properly connected, everything will work just fine. Up until now, almost all my projects have used ESP Home. It's perfect fit if you plan to control the device through Home Assistant. It even supports shift registers, which is a key part of this project, so you can absolutely use it if you want. However, the biggest strength simplicity, can be also a bit of a downside. ESP Home comes with quite a few limitations. For example, you have to use Home Assistant if you want to configure or change anything. If you want to unlock the full potential of the ESP32, you'd have to go a level deeper, a level closer to the metal. And that's exactly what I did in this project. Instead of using ESP Home, I went with ESP-IDF, which is Espressif official IoT development framework for ESP32. That doesn't mean you can't use this display with Home Assistant. You absolutely can. And even better, you can control it really at the same time from Home Assistant and directly through my web app. You don't have to reflash or anything. Speaking of programming, to flash ESP32, you need a USB UART adapter. You can get one on Amazon for cheap. The flashing procedure is super straightforward. Hook up the VCC to VCC, GND to GND, RX to TX, and TX to RX. Open the Flash Download tool, load a few binary files, click Start, and you are done. I'm not gonna bore you with all that nitty-gritty here. There's a full step-by-step guide on my website. Once it's flashed, the device is basically plug and play. From that point on, all configuration happens in the GUI. Also, you can toss the programmer into a drawer, because once the device is online, you will be able to update the firmware remotely. Before we dive into the display modes in detail, let's cover a few general things first. When you power on the display for the first time, it boots up with Wi-Fi in access point mode. That means it creates its own hotspot. Just connect to it. Then open a browser and go to this address. Once the page loads, you've got a full control of the display. You can set the time zones, split it into groups and assign modes. But I figured that wouldn't be very convenient long term. You'd have to keep switching from your home Wi-Fi to the display's hotspot just to make a tiny change. So go to the Wi-Fi setting, switch to the Wi-Fi client mode, enter your local network's SSID and password and hit save. The device will save it, restart and connect to your home network. From that point on, it'll boot up straight into Wi-Fi client mode by default. No more hopping between networks. As for remote updates, when a new firmware is available, you'll see a notification here. If you want to install it, just click Update and wait a moment. The device and the web app will update themselves and restart to the latest version. Now moving to the main part. At the center, you'll see a graphic representation of your display. The number of modules shown depends on how many are physically connected to the main module. When the ESP32 boots up, it automatically detects this and sends the info to the app. So there's no need or way to configure it manually. Below, there's a drop-down list with all the modes. The size of that list depends on which modules it controls. Right now, it spans to the entire display since there's no group set up yet. And since we are on the topic, the display can handle multiple tasks at the same time. To make that happen, you need to divide it into groups. Let's say you've got 6 modules and you split them into 2 groups, Group 1 and Group 2. One of them could, for example, show data from Home Assistant, while the other could fetch info from the internet like current commute time to work with real-time traffic, stack quotes or anything else you want. You can think of them as separate displays. They have to be physically connected, but they work independently. To create groups, just click the red plus icon between 2 modes. Whether the separator shows up as a space, colon, dot or a dash, it's purely visual choice. Now you'll see 2 completely independent mode selectors, one for each group. You can keep dividing it into as many groups as you want. To remove the separator, just click on it again. Alright, let's go through all the modes one by one. None. This is a default state and it's useful when you don't want to use a particular group doing anything. When you activate it, all segments turn off, no matter what was displayed before. Manual. It lets you to display anything you want. In this mode, you can click on individual segments to turn them off or on. This way you can create any symbol or word you want. MQTT. This is what you want if you are planning to hook up the display to Home Assistant or really any other system or app that supports MQTT. Just add your MQTT broker info and user details into the setting window. You'll find the IP address here and the port number here. By default it's 1883. The last step is to give your topic a name. Think of a topic like an address. Home Assistant sends it before the actual data. If your display is listening for that topic, it will receive and show the message. If not, it will ignore it. Timer. Just like the name suggests, this mode is all about counting time. I made two versions of it. The first one is a simple timer that can count up or down at any interval you want. And more advanced one where you set up the work time, the rest time and number of cycles. Both versions have an alarm option. When enabled, after the timer reaches its end, it will start clapping, using the display's natural clicking sound. I didn't come up with this idea myself, thanks Flower, but I loved it so much I decided to bake it right into the timer mode. Clock. It works both as a clock and a calendar. All you need is to pick your time zone and you are good to go. The main module has an RTC chip and battery backup, so if the power goes out, the clock won't lose track of time. As soon as the power comes back, it resets itself to correct time automatically. That's actually one of the reasons I added the LED, to give you a quick visual check on whether the time is accurate. Custom API. This mode lets you to fetch any info from the internet via an API. So, let's say you want to check exchange rates from a bank. Instead of manually visiting the bank's website, your app sends a request to the bank's API and gets just the data it needs. Some APIs are completely open, where all you need is the address. Others require an API key, which usually means creating an account to the provider's website. And this mode should be able to handle both types. You can also set up a filter to extract just a specific value you are interested in. And before you committing to anything, you can test your setup to make sure it's pulling exactly what you want. And that's a wrap on the display modes. Once you send the config, you can close your browser, kick back and watch your 7-flip display do its thing. Thanks for sticking around till the end. I hope you enjoyed this video and see you next time.